So welcome back everyone. In the last class we had seen how to get Hamiltonian for an RF pulse uh, with an offset which is given by capital omega and with a phase angle. So what I mean is, like, if you have, let's say, in Cartesian coordinate system, as we have learned, if we draw, this is the B1 field and this is my offset, which is also given by delta B naught, right? And this is the phase angle. Then Hamiltonian in rotating frame can be written by omega Iz. This omega is the capital omega given by this small arrow in the z-axis, plus omega 1. Now this omega is omega 1 is corresponding to the B1 field, which is generated because of the RF pulse. Okay, and this is Ix cos phi plus Iy sin phi. So this we have learned how to derive in rotating frame, right? So this is a general expression of for any Hamiltonian for any RF pulse. Okay, so let us say for example, if we want to have Hamiltonian for an on resonance pulse with let's say Y phase. Okay, so in that case omega will be 0, and for Y phase what we will have, so if the phase has to be, so that means B1 has to apply along Y axis as in here, then phi has to be 90 degree, right? So if phi is 90 degree, what do I have? I will have H is equal to omega 1 Iy, because Ix term will go to 0, cos 90 will be 0, and I'll be left with only sin 90, which is 1, so I will have omega 1 Iy, right? So this is a on resonance pulse with Y phase. Similarly, if you want to have a on resonance pulse with X phase, I will have omega 1 Ix, right? So typically in most NMR experiment, pulses which are applied are most either X phase, Y phase, minus X phase, or minus Y phase. However, in certain experiments, which are although rare, phases can also be of 30 degree, 45 degree, anything, any random phase, 225 degree, 105 degree. Although for the discussion for this course, we will be only discussing pulses which are of either X phase or Y phase. But that doesn't stop you to explore what happens if we apply a 45 degree phased pulse, or 225 degree phased pulse, or any random phased pulse. Okay, but we will restrict our discussions to X and Y phase. Okay, now let us say that you want to understand the effect of an RF pulse. So as of now we know what is the Hamiltonian during an RF pulse, right? But now that let's say you want to understand the effect of an RF pulse on evolution of density matrix, right? So as we have learned that density matrix evolution is important to understand how NMR experiment is proceeding. So now you want to understand effect of an RF pulse. So let's say a RF pulse is expressed like this. Now here there is some density matrix, let's call it as delta sigma 0, and this is a RF pulse during which Hamiltonian is, let's say, HRF, right? And after the RF pulse has been applied, the density matrix evolves to sigma 1. So this is called as time evolution of sigma, right? Which, if you remember, which is given by sigma t is equal to d sigma by dt is equal to minus I h sigma t, right? The Liouville-von Neumann equation, solution to which was given by sigma t is equal to e to the power minus I h t sigma 0 e to the power I h t, right? So in this case, the Hamiltonian will be the one which is given for the RF pulse, and sigma 0 is the one which is just before the RF pulse. Time is the duration for which this perturbation is applied, the RF perturbation. So this will be tau p in this case, if the pulse is applied for, let's say, tau p duration. Then sigma t is nothing but the sigma 1 at the end of the pulse, right? So that's how you can calculate evolution of density operator as if the perturbation is known. So in this case, the perturbation is RF. So here, for example, we know what is sigma 0. So let us say that if we know sigma 0, if we know what is HRF, if we know what is TP, or the time duration for the pulse, then we can calculate what is sigma t, right? So that is easy to calculate. So this we already are aware of. We have seen what will be the Hamiltonian for an given RF pulse. This, for example, for a Y phase pulse, for a X phase pulse, we calculated that, right? The duration, we are setting up the experiment, so we know the duration for how long we are setting up the pulse for, right? RF pulse for. Now the question is, how do we know what is sigma 0? Okay, so let us say that we have placed the sample inside the magnet and the sample has attained thermal equilibrium, right? So thermal equilibrium, which is nothing but creation of the Zeeman states. Let's say if we are talking about spin half system, so we will have two spin states where population of spin state alpha will be greater than population of state beta, right? This we have learned. So this is the state of thermal equilibrium. Okay, now at this state we want to know what is sigma 0. Okay, or we can call it as or let's call it as sigma 0 only. So this will be the equilibrium density operator, right? So our goal is to start with if we know what is the equilibrium density operator, then of course we can find out the perturbation and calculate the time evolution of density operator as a function of that perturbation. So, but the goal has to be the identification or the estimation of what is our equilibrium density operator, that is at the start, before the start of the experiment. So what we have done is we have just placed the sample inside the magnet and we want to know what is the density operator of that system at that particular instant. Okay, so let us consider the ensemble of a spin half system. So it's a single spin, so there is no spin-spin coupling here. So it's a simple case of a single spin. The example can be, let's say, water molecule, which has only one type of proton, so only a single spin half, but it's an ensemble of that because there is Avogadro number of spins which are present in water sample, right? Okay, so let us consider that this is our system and now we want to calculate the equilibrium density operator. So we can understand that, as I just mentioned, that the population in the two stationary states can be given by Boltzmann distribution. Once the thermal equilibrium has been achieved, the population in the two states will be given by the Boltzmann distribution. Okay, so thus the density operator at thermal equilibrium, sigma EQ, can be understood that it's a probability of being in a particular state. Okay, so we can also understood this. Let's consider for a uh, spin half state. It's a general state which is let's say C alpha alpha plus C beta beta. Let us say that if it's a general state, okay, any given superposition state, now the uh, the projection operator or the probability density will be given by ket psi and bra psi, which will be given by C alpha alpha, or we can actually write it in the matrix form first and then do the multiplication. It will be easier for us. So let's say, so alpha is given by 1 0 and beta is given by 0 1. So then I can write this as C alpha C beta, right? So I can write alpha is 1 0, multiply this C alpha goes in, C alpha 0, and then if I take the addition I will have C alpha beta, right? So this is my ket psi. Now then my bra psi will be transpose and conjugate, so this will be C alpha star C beta star, right? So this will be a row matrix, this will be a column matrix. Now if I take the probability density or the projection operator, this will be the inner product between so ket psi and bra psi. So this can be now written as, so you have C alpha C beta C alpha star C beta star, right? And now what I'll have here is 2 by 2 matrix where I will have C alpha star, then I'll have C alpha C beta star, C alpha star C beta, and C beta star. So now you can understand that these are the population terms. We have understood earlier, we have learned earlier that mod of C alpha or C alpha star, it's not is the probability of finding a spin in state A, right, in state alpha. Similarly, this is probability of finding spin in beta state, and these two are called as coherences. So this is the population, that is the population in alpha state and population in beta state. This is the transverse population, that is the coherence, so which is a mixture of alpha and beta state, right? So this is pure alpha, pure beta, right? So this is given by population. This is called as population, right? And this is called as coherence, right? Okay, or the transverse magnetization part, you can say, right? Okay, so now here this is what I'm writing. Now if I convert this into density operator, I will have the ensemble averages, and then this will get converted into density operator. So this is nothing but we have seen this earlier, so I just wanted to remind you of that density operator is given by when there is a thermal equilibrium, when we know that there is no off diagonal element, there is no coherence, there is no transverse component of the magnetization, there is only longitudinal component which is which just gives you the population, the probability of being in a particular state. The density operator is given by Cn star, and then the ensemble average, right? Okay, so now we can write density operator as, because this is just the population, so we can write the Boltzmann distribution, which is given by e to the power minus I En, which is the energy of the nth state, kBt is the Boltzmann constant at that temperature, divided by summation over all states, and I'll have e to the power minus En divided by kBt. Right now, if I expand this using Taylor's expansion and apply high temperature approximation, I can write this as 1 minus En divided by kBt, and because this is for n states, I can write it as 1 for each state, so 1 plus 1 plus 1 plus 1 up to n, right? So that means this becomes, so this is assuming that my En is very, very small than kBt. As I said that this we have done earlier, high temperature approximation, right? So now we can reduce this to 1 minus e to the power En, that is the energy of the nth state, kBt whole divided by n, right? So n is nothing but the number of states. So if the number of states are 2 for a spin half system, n will be 2, so you will have 2 here, right? Okay, now in operator form, I will replace E with the corresponding operator, which is Hamiltonian, and 1 with unity operator. So I will have sigma EQ as operator n cross n divided by n minus Hamiltonian divided by n kBt, right? Okay, so for a spin half system, I can write this will be identity operator of order 2, because the total number of states will be 2 divided by 2 minus Hamiltonian 2 kBt. Okay, this is nothing but number of states. Okay, now so this is the form of equilibrium density operator. Okay, now this H is nothing but, I can further simplify this, 2 cross 2 divided by 2 minus H can be written as omega I Iz divided by 2 kBt. Okay, this is the Larmor precession frequency containing the chemical shift, containing the shielding constant term. Okay, so all of this will not be operated on any of the operators, right? Later on we will see any of the perturbation will not be affected by any of these constant terms. So thus we can only talk about this part. Okay, so this can be multiplied later on with the answer whatever we get when perturbation is applied on sigma or the equilibrium density operator. So thus we need not worry about this. This is only to simplify maths, that we will call sigma EQ as just simply Iz. Okay, and this is for a single spin. If you have multiple spins, let's say, that is, let's say if you have CH3 CH2 OH as your sample, then you have 3 types of protons. So then my sigma EQ in this case will be Iz for CH3 plus Iz for CH2 plus Iz for OH. Like each proton will have its own density operator, and the total density operator will be summation of individual spins, right? So that is simple to understand, and I hope this part is very, very clear. So now we know what is density operator at starting, what is the density operator for the perturbation. So thus we should be able to carry out an experiment, NMR experiment, and see how density operator is changing with time. What is the time evolution of density operator? So let us consider a one pulse experiment. So one pulse experiment for a single spin half system. So that is, we are only considering this thermal equilibrium's density operator, right? So one pulse experiment can be typically shown as so where this is the thermal equilibrium part. So here thermal equilibrium is being achieved or has already been achieved, and the density operator is given by thermal equilibrium equal to Iz. This is the RF pulse, we all know that now, and here the Hamiltonian is given by HRF is given by small omega, capital omega, Iz plus omega 1 Ix cos phi plus Iy sin phi, right? This also we have seen. After this, after this RF pulse, the density matrix will evolve to, let's say, sigma 1, and during the acquisition time the Hamiltonian will be, in this case there is no spin-spin coupling, so there is only chemical shift Hamiltonian, which will be omega I Iz, right? And after the end of this, the density matrix will evolve to sigma 2, right? So what we have to do is we have to calculate sigma 1 because of perturbation of RF pulse on to sigma EQ, then followed by this chemical shift evolution on sigma 1, we will calculate sigma 2. Okay, so that is our goal, to see what is happening, how density operator is changing because of these two Hamiltonians. One Hamiltonian is RF pulse Hamiltonian, another Hamiltonian is chemical shift Hamiltonian, right? And once, let's say, once the experiment is finished, at the end of the experiment, what we are trying to measure here, so we are trying to measure the expectation values of Ix and Iy, right? So what we are interested in, the transverse magnetization, how that magnetization is changing, right? So like in block description of NMR, we were interested in understanding mx and my, evolution of mx and my term, right? So we were interested in finding what is dmx by dt and dmy by dt, right? So here we will be looking at the expectation values of Ix and Iy, and that basically is given by I plus operator. So we will be measuring this. So to measure the expectation value at the end of this experiment, what we have to simply do is this, we have learned. All we have to do is take trace of sigma 2 into I plus. So find the matrix sigma 2 into I plus, take a trace, and that will be your expectation value. Okay, and that will be your measurement, basically, that what is happening with the transverse magnetization by the end of the experiment. All right. Okay, so now let us start with sigma EQ. So I will not do the complete calculation because now you all are aware of what is the solution of Liouville von Neumann equation, how to apply BCH formula. So let us do a shortcut calculation. So let's start with sigma EQ equal to IZ, and let's say my RF pulse is a on resonance X pulse. Okay, so that means I know the phase value, I know that capital omega is 0, so this is on resonance X pulse now. All right, so this means sigma 1, which is after the end of the application of RF pulse, is given by e to the power minus I h RF, and the total duration during which for which the pulse is applied goes here, which is tau p sigma EQ e to the power I h RF tau p. So I have directly written the solution to Liouville-von Neumann equation. Okay, don't get startled by looking at this. So I have simply written the solution to Liouville-von Neumann equation, where Hamiltonian is the RF Hamiltonian, sigma 0 is nothing but the sigma equilibrium, that is the thermal equilibrium density operator. Okay, so now let's plug in the values and simply carry out the BCH expansion. Okay, let's do that. So sigma 1 is equal to e to the power minus I omega 1 tau p. So this is the Hamiltonian part. Then I will write this is the complete Hamiltonian part, and the tau p. Tau p is nothing but the duration for which this is applied. And then my sigma 0 was IC e to the power plus I omega 1 tau p Ix. Now you can also see that omega 1 into tau p is nothing but the angle alpha, which is the flip angle. Right? So if you remember, this is how far you are flipping down the magnetization m0 x y z. So if you carry out this rotation Rx, by how far you are flipping down this magnetization, this angle is called as alpha, or the flip angle, right? Okay, so now let's try to expand this using BCH expansion. So what we will have is sigma 0, that is IZ, minus I, and then omega 1 tau p will become alpha. So I will have I alpha divided by 1 factorial, then commutator between Ix and Iz, plus I alpha square by 2 factorial, and now I will have double commutator Ix Iz minus I alpha cube by 3 factorial Ix. Now I will have triple commutator Ix Iz. So now this part I'm not going to solve for you, because we have already spent a lot of time on understanding what is BCH, how is BCH expansion solved. So I'll just make use of the following thing, that Ix Iy commutator is equal to Iz, and if and this is cyclic, right? So that means if I have Iy Ix, this becomes minus Iz, right? So when I do that, what will I get? I will get Iz cos alpha minus Iy sin alpha. Okay, so I will request you to do this complete calculation as home assignment and see if you are getting the same answer. Okay, so try to go from here to here and see if you're getting this answer or not. So this is your sigma 1. Now I'm choosing my tau p. So I am choosing my tau p so that alpha is equal to pi by 2 or 90 degree, right? So I can always do that because my omega 1 is fixed, so I can perturb my tau p, so I can choose my tau p so that my alpha is, or the flip angle is 90 degrees. So that means the magnetization is flipping down to the transverse plane. So this will give me sigma 1 as, so if I do cos 90 will be 0, sin 90 will be 1, so this will become minus Iy. And now this is very clear that how rotation about x-axis, because the pulse phase was x, so this is a rotation about x-axis takes m naught to minus y-axis, right? Okay, so sigma 1 we have calculated. Now let us calculate sigma 2. So now the perturbation is the chemical shift Hamiltonian, right? E to the power minus I h chemical shift for a duration of t acquisition time, and I will have Iz as the Hamiltonian, right? And here I have sigma 1 and then plus I chemical shift. So this Iz will actually come from chemical shift itself, t acquisition. So this is for the duration of acquisition time. Okay, now what will I have here? So this will be e to the power minus I omega I Iz and t acquisition, and instead of sigma 1 I will write now minus Iy and e to the power plus I omega I t acquisition Iz, right? Now again I'll just write down the BCH formula part. So I'll have negative sign which I'll take out, then Iy minus I omega t by 1 factorial, and I will have commutation between now Iz and Iy plus I omega t by 2 factorial, this is square, and I will have double commutator Iz Iy minus I omega t cube by 3 factorial Iz. Now I'll have triple commutator Iz Iy and so on. So again finish this calculation yourself. Try to, it's just plugging in the numbers, finding the commutators, and carrying out this simple calculation. So the answer to this will be minus Iy cos omega t plus Ix sin omega t. Okay, so this is the result of the experiment. Now let us do the measurement. So our measurement is nothing but finding trace of the matrix sigma t, that is sigma 2 here, into I plus, right? So because we wanted to measure the expectation value of I plus, so this will be given by trace of sigma 2 into I plus. Now what is my sigma 2? Sigma 2 is this. So let us and then what is my I plus? So let's first calculate what is I plus. I plus is nothing but Ix plus Iy, right? So I know the matrix for ix. What will be the matrix for ix? Ix is in natural units. I am assuming h cross is equal to 1. So ix is 0, 1, 1, 0. Similarly, iy is nothing but I by 2, 0, minus 1, 1, 0. So once you plug in these numbers, you can easily calculate the matrix multiplication. So I will not do this matrix multiplication for you because this is too simple. It's a 2 by 2 matrix, you should be able to do that. So you know the matrix form of sigma 2 because you have this with you, sigma 2. You know the matrix form of I plus operator because you have ix and iy. You can plug in these numbers, carry out this multiplication, find the trace. Trace is nothing but sum of the diagonal elements, and that will be your expectation value. So what is that expectation value? That answer I will give you, and please do the calculation and see. Otherwise, I will ask you how do you do that in interaction session, and the answer would come out to be minus 1 by 2 e to the power minus I omega t. Okay, so that is your that is your answer. Okay, so of course we have not discussed in this one the relaxation component. If we want if we also include the relaxation Hamiltonian during the acquisition period, what we will end up having is minus tr2. Okay, so that part we have not done. Maybe if we get time, I'll show you how to do that, but it is again simple and straightforward. So let's try to do this part and see if you are able to get this answer. So this is nothing but now we have the evolution part, and this is the relaxation part, right? So if you remember the block equation discussion, we had the similar form of the signal. So where we had, if you remember, that m plus was given by m0 with the evolution part and the relaxation part, right? So the forms were very, very similar, and now using the quantum mechanical picture also we have arrived at the similar conclusion that the NMR signal is of this type of form where the evolution is happening at the offset frequency followed by the relaxation, right? Relaxation part. Okay, so now let us quickly summarize what we have learned so far. So we know that the equilibrium, now we know that the equilibrium density operator is given by, or we'll write sigma eq can be thought of Iz. Of course, there is the other constant terms which we are not worried about at this point of time. Then time evolution of density operator is given by d sigma t. These are the key equations that we'll be using very frequently, so I'm just writing it over here, minus I h sigma t, right? Then to this, this is Liouville-von-Neumann equation, and the solution to this equation, provided the Hamiltonian is time independent, is given by e to the power minus I h t sigma 0 e to the power plus I h t, and this can be also expanded, using BCH formula, right? So that is easy to see. Also, the observation at the end of the experiment is done by finding the expectation value of the I plus operator, and which is given by trace of sigma at the end of the experiment into I plus. Free precession Hamiltonian, that is during acquisition, what will be the Hamiltonian? Free precession Hamiltonian H is given by omega I IZ, and plus, of course, if you have two spin system, it will be omega S SZ and so on, right? Then RF Hamiltonian, this is given by offset IZ plus omega 1 Ix cos phi. This is again a general Hamiltonian. You can find out if depending on the offset and the phase value of the pulse, what will be the exact Hamiltonian, right? I phi sin phi. So given this, you should be able to calculate the result of any particular NMR experiment. Of course, we have not discussed yet the Hamiltonian for spin-spin coupling, for example, Hamiltonian for relaxation. So that we'll try to cover in later classes. So now let's, after the summary, let's also make a key observation which makes your life easier. You don't have to go through all this calculation. So this is the whole calculation, and then the summary of this calculation is again I'm just trying to write over here a key observation. If you have IZ operator, let's say this is your sigma EQ, right? And you apply a Hamiltonian or any perturbation, so the resultant of this will be old operator so this of course is deduced from the previous all the calculations what we have done. Cosine of angle, so here angle is given by frequency into time. So frequency is the frequency for the perturbation, and time is during which the perturbation has been applied. We will see an example just now. Okay, old operator and then new operator sine of the angle. The angle is given by the same frequency into time, right? Okay, so now let's say how do you calculate the new operator if the old operator is given? So this is simply given by a cyclic relation between Ix, Iy and Iz, and that we have already learned that the commutation between Ix and Iy gives you Iz. So I'm just simplifying it further. Ix operating on Iy will give you Iz, Iy operating on Iz will give you Ix, Iz operating on Ix will give you Iy. So let us see that example, and if you do it in the reverse cyclic manner, then you will get a negative sign and nothing else. So Iz operating on Iy will give you minus Ix. So let us take this exact same example that we have solved earlier, like previously in this lecture. So your starting density matrix is Iz, and you had applied a 90-degree x pulse, right? So that means your Hamiltonian here is Ix, and your duration, that is omega 1 tau p, is equal to pi by 2. That is, your angle is pi by 2, your Hamiltonian is Ix, right? So this is what you need. So now Ix is being applied on Iz. Okay, so Ix is being applied on Iz. That means your new operator will be minus Iy here, right? So old operator is what? So old operator is same as Iz, then cosine of 90 degree, angle is 90 degree. The new operator is Ix operated on Iz gives you Iy with a negative sign. Negative sign because it is now going in the reverse cyclic manner. Then sine of 90 degree. This is nothing but minus Iy, and this is what you got as sigma 1, right? This is your sigma equilibrium. So now further for sigma 2, so after this I'm doing a chemical shift evolution. So Hamiltonian here is omega I Iz, and the duration is t acquisition time, right? So what do I get? My old operator is minus Iy, cosine of angle is omega I into t, frequency into time, right? New operator will be, now Iz is operating on Iy. So if Iz is operating on Iy, again I'm going in a reverse cyclic manner. So I will get minus Ix. I have another minus here. So that means plus Ix. And I will have sine of omega I Iz. Sorry, omega I t. Right? So this is what I have got as sigma 2, which I got earlier also. So the whole problem actually became very simple once you identify that any given operator upon any kind of perturbation can be thought of as old operator into cosine of that angle plus new operator into sine of that angle, and once you understand this, you can actually carry out any perturbation in NMR. So all the perturbations in NMR are basically doing rotations about different axes, and for a particular amount of time with a particular amount of frequency. So if you know the frequency and time, you know the angle. So that means all you have to do is you have to find out what is the old operator, what is the angle, do a cosine angle, what is the new operator using this setup, and what will be the sine of that angle. Okay, so I think that is all for today, and I hope that Onepulse experiment is very, very clear in the heads. And in the next lecture we'll try to look at multiple spin system, and we'll try to also introduce the spin coupling Hamiltonian. That is all for today. Thank you.